In this video, we have another example of a chi-squared test in action. We're going to be using problem number 10, which is visible on the screen in front of you right now. It's titled Health and Education, and if you read it, it says as follows. Does amount of education play a role in the healthiness of an individual? The following data represent the level of health and the highest degree earned for a random sample of individuals from the General Social Survey. Now, one thing that's very confusing to people as they go through this particular section, they have a really hard time to know, am I doing a test for independence or am I doing a test for homogeneity of proportions? And so that's something we're not expecting you to be an expert in, and it can be very subtle sometimes, but we are expecting that you would think about it and would hopefully have some kind of an idea of how to answer. Let's look at an example. In this particular case, we're trying to decide between testing for independence and testing for homogeneity of proportions. Now, when you test for independence, you're testing for a single population. Let's put it that way. All right. So in other words, you have individuals from a single population, and you have two different variables associated with those individuals, and you're trying to find out whether those variables are related in some fashion or not, whether there is an association between the variables. For homogeneity of proportions, you're testing individuals from two populations. And I understand, how do you define a population? That can be subtle, okay? That can be difficult, and it can require some kind of a case, but we're not expecting you to be an expert in this one section. We're just expecting you to look at it and have some idea of, okay, I think it's this or I think it's that. And to be direct also, if you were doing this on an exam where the problem was stripped of context, the calculation process for both is the same. And so if you approach the question and you put down, say, the wrong hypothesis, let's say, for example, it was an independence test and you thought it was a homogeneity of proportions, and so you put down the wrong null and the wrong alternative hypothesis. As long as you have everything else recorded, you're still going to get a substantial amount of partial credit for the work. Because again, the calculation process is the same, and yes, it can be very difficult to distinguish between the two in a survey course like this. Let's go back to our example. Now, one dead giveaway in this question here is the wording of part A. It says, does the evidence suggest that health and education are related? And so that is a way of asking, are they independent or not? At the same time, when you look at the contingency table and you see the data that it contains, you only have one population here. You have individuals who have levels of education and levels of health. And so it's not two populations, and it would not make sense for this to be a test for homogeneity of proportions. It's independence. Now, what you see in front of you there is the observed counts. And so, as you may recall from the previous example, we need both observed and expected counts, and we want to see how are we going to get those expected counts. Now notice there is no marginal distribution provided in this case, so you'd have to come up with that. Here's what you get. So I have my observed counts in black, and I have my marginal distribution shown in blue. And I had to do a little bit of abbreviating here for obvious reasons. I don't have a ton of real estate on my screen, and so I have to try to squeeze it all in. And this is a large contingency table. And so I have across the top X for excellent, G for good, F for fair, P for poor. And on the vertical column, I have less than high school, I have high school, I have community college, BS stands for bachelor's degree, and G stands for graduate degree. And so if you compare that with what we have in the text, you can see that they match up. Now, it's not explicitly stated in the problem here. They don't ask that you check that the conditions are satisfied, but that's kind of the standard operating procedure. It's assumed that if you're going to do a problem like this, you know how to avoid garbage in, garbage out, and that means you know how to check the conditions that are required. What conditions are we talking about? Let's take a quick look. The specific conditions that I'm referring to are listed here under Part B of Step 3. Condition 1 reads, all expected frequencies are greater than or equal to 1. And Condition 2 says that no more than 20% of the expected frequencies are less than 5. Now, obviously, a key phrase there is expected. And so we're not talking about the observed frequencies. We're talking about the expected frequencies, which we have yet to obtain. And so we need to get those, and we need to have them in the calculator, and probably not a bad idea to have them written down as well. You can see the rest of the parts of the problem there. There's some things that are going to be asked. So anyway, let's get about getting those and getting everything keyed in. Now, if you recall, the calculator is going to be holding the data in matrices. And so in order to get it keyed in, we would go as follows. We go to the matrix submenu. And I'm going to be using matrix A for my observed counts. And if you look at the size of the contingency table, it has 5 rows and it has 4 columns. And so the size of the matrix that we need to enter would be 5 by 4. And at this point, we are ready to key in the data. Go ahead and pause this and take a look if you will. But anyway, those are my observed counts. And so I am then ready to put in my expected counts. You want to quit here. Go back to the matrix submenu. And we are going to be editing now matrix B. So notice that I have number 2 highlighted right there. And when you press enter, we are then ready to key in the dimensions. Matrix B and matrix A have to be the same size for this test to work, obviously. And so it's going to be also 5 by 4. Now, as far as entering those expected counts, it may seem a little bit redundant, but we do like to have a written record. And so if I'm working this out on my own, I typically I'm doing 2 things at once. So on one hand, I'm using the heavy lift. I'm using the calculator to do the heavy lifting for me. All right, meaning I'm doing the calculations here on the fly and keying them in. And then I just write down what I need. And so I'll show you both, but we definitely are looking to have a written record. And if you're looking for some kind of a model, how's it supposed to look? It looks like the examples in the text. I find that works very well. And if I'm teaching this using a whiteboard, I typically do a little bit of color coding so that everything is kept separate. So like in this case, I'm going to write down my expected counts in red, and I'll show you in just a moment what they are. But let's get a couple of expected counts again to remind you. How do you do that? As you saw in the previous example, there's sort of an abbreviated way that we go about calculating this. We use the row total times the column total, and then we divide that by the table total. And so obviously it's kind of hard to do that if you don't have the marginal distribution laid out in front of you. And that's why I did that first. And so I will get that keyed in, and if you're following along, I'll put it up on the screen so you can also work on getting that keyed in. And then hopefully at the end of that little segment, we will both have the same thing in our calculator, and you'll be closer to having the test finished. So let's get that done. So you can see the very beginning of it right here. And where did that value in red come from right there? 148.64. Well, I took 535, I multiplied by 976, and I divided by 3513. And then I recorded it to 2 places. Usually when I'm writing it down, I'm going to use 1 place or 2 places as space permits. But of course, when I'm calculating it on my calculator, everything is recorded to the full precision. Not that it makes a huge difference, but anyway. So let's commence with the rest of that, and hopefully you'll have the same as me at the end here. Go ahead and pause the video and follow along. So here's what I have. Again, I have a written record, and I also have it in my calculator. And so the observed counts are in black. The expected counts are in red. And as far as the conditions that we were talking about, let's make sure that both of those are satisfied before we move over or move back to the calculator. So again, the conditions are that all expected frequencies are greater than or equal to 1, and that no more than 20% of the expected frequencies are less than 5. And so I'm looking at my expected frequencies, and it looks like both of these conditions are satisfied. of the expected counts in red are greater than 5. And so we're good. I can check off both of those conditions as being met. And so I'm just putting a check mark there to indicate that. Now we need to have all this in the calculator, which I do, and so let me switch over to the calculator. So here, as you can see, are my expected counts, and hopefully you match on that. At this point we are ready to run the test. So we quit this, we go to the stat menu, we go to the test submenu, and we're looking for the chi-squared test, letter C on this menu. Everything is in place. All we have to do is calculate. And there's our results. Now, before we jot this down, just take a quick note. That p-value is exceedingly small, and so we will definitely be rejecting the null. And you know, that was kind of obvious actually from the very beginning if you go back and look at our table here. Let's jot down what we've got, and also let's take a look at why I would say that. Speaking of the null hypothesis, what is the null hypothesis and what is the alternative hypothesis? Well, as you can read, for the generic test of independence, the generic null is that there is independence, and the generic alternative is that there is not. Put differently, for this particular situation, our null hypothesis is that there is no association between education level and health, and our alternative hypothesis is that there is an association between education level and health. And as we saw, we got a test statistic, a very large value of 285.061, and our p-value was exceedingly small. It was 6.391 times 10 to the negative 54. And so as far as a conclusion is concerned, well, the p-value is smaller than alpha, which means we're going to reject the null hypothesis. What does that mean practically speaking? Well, it means that there is an association between education level and health. And what precisely that association is, well, that's part of it's another part of the problem. So anyway, let's state what we have here, and we'll put it in context. If you want to state our conclusion in practical terms, we're saying that the evidence we have supports the claim that education level and health are, in fact, related. Now let's take a look at the rest of the question. So what we just had on the screen there is our response to part A, which is asking, does the evidence suggest that health and education are related? And our answer is yes, they are. And we rejected the null hypothesis. Now part B is asking for a conditional distribution of health by level of education. And the key there is the by level of education portion of the phrase. That means that they want us to use the row sums of the marginal distribution as denominators when we construct that conditional distribution. And the reason we want that is because we want to look at the proportions in each of the cells. And it's not just any proportions, but we want to look at it conditioned by education level. To put it differently, what we're saying is we want to look at, for example, in the row that is covering the bachelor's degrees, we want to know what proportion of bachelor's degree holders are in excellent health, and what proportion are in good health, and what proportion are in fair health, and so on. And likewise for each of the rows. Now this does take a little bit of calculating, but it's not that big of a deal, so let me switch over and show you what I have. Here's what I have. If you look carefully, I'm trying not to make the screen too cluttered. And so if you look at the first row as an example, you'll see that less than high school, when I calculated this, I was using the row sum of 535 as my denominator. And so I showed the calculation for the first cell, and I did the same thing in each of the rows. For the subsequent cells, I left them with just the value. And so if you go back to your original observed counts, and you use those as your numerators, then for the first row you'd be using a denominator of 535, for the second row 1808, and so on. And so if everything goes according to plan and you record everything to 3 places, this is roughly what you should see. And so again, they are asking us, well, what is the association? I mean, what's the relationship between education and levels of health? Levels of education and levels of health. And so you sort of notice a trend, if you look carefully. You'll notice that in this first column here, with regard to excellent health, people who have a higher level of education, a much higher proportion of them are in excellent health. And conversely, the lower the education, the lower the proportion. So if you're comparing the extremes, here you have about 0.418. So in other words, almost 42% of the individuals have excellent health when they have a graduate degree, whereas only about 13.5% of the individuals with less than high school have excellent health. And that trend is carried across to the other extremes as well. So if you're looking, for example, at poor health, you'll notice that a very small proportion of individuals with a higher education have poor health, and the proportion of people who have a low level of education is much higher. And in fact, if you wanted to calculate the ratio, you could take 0.116 and you could divide it by 0.006. It is, it's about 18 times higher, maybe about 17 times, something like that. So there's a very clear association here. And if you wanted to capture it in a sentence, you could say something like the following. There's no one answer that's correct to this, but what we're looking is to capture overall what's happening in the contingency table in the conditional distribution. And so here would be a possible response. I'm saying that the conditional distribution shows that higher levels of education tend to correlate with better health. For example, only 13.5% of the sample with less than high school reported excellent health versus more than 39% of individuals with at least a bachelor's degree. So greater than or equal to BA/BS there at the end is saying basically a bachelor's degree or higher. And that is what the table showed. Now, of course, you could say the same thing using similar words in many, many different ways. So I'm not saying that you have to say it exactly this way. But that's a representative answer. And, the same thing is evident in other parts of the table, sort of depending on what you want to fixate on. Now, let's make sure that we're done with the question here. If you look again at what it's asking, we've answered part A. And we've pretty much answered part B. It says construct a conditional distribution, which we did. But it also asks you to draw a bar graph. And I wanted to mention that even though it asks this is not something that I would typically ask. The reason being is that it's not convenient for us to produce it. We're not using SAS or Minitab or something like that, or Excel. And we're not going to be using that. We're using a graphing calculator, and unfortunately, the graphing calculator doesn't do a bright and shining job of those types of bar graphs like we would need for this one. And so we're not going to bother you with that. If you are confronted by this type of a question on MyLab, you'll find that it's generally multiple choice, and so it's not that hard to field. And if we want you to have a bar graph like this on an exam, we would give it to you. So we're not going to ask you to produce that. Now, regarding part C, it did say write a few sentences that explain the relation, which we just showed you. And again, you could say that several ways. There's a follow-up question here. It says, can you think of any lurking variables that help to explain the relation between these two variables? And I'd say, well, yeah, off the top of my head, generally speaking, one's earning potential tends to correlate with the level of education. So in other words, the more education you have, the more you tend to do in terms of earning potential. The more you tend to have, the more you tend to make. And when you're making more money, you have better access to healthcare and insurance and all that sort of thing. And so this is not surprising. We are not suggesting with this that all you need, the key to good health is more education. That's not the case. The key to good health is taking care of yourself, but also having reasonable access to medical care. Anyway, I hope that's helpful. And so if you have any questions about this, feel free to drop me a line. And we have a couple of other videos for you from other examples from this section.